Hello everyone, I'm going to talk about streaming and massively parallel algorithms for edge coloring. Our first result is an MPC algorithm that using of n space per machine and of m total space returns the 1 plus little o1 delta edge coloring within constant number of rounds. Our second set of results are in the streaming model. We show that if the edges arrive in a random order, we can achieve an of delta edge coloring using n polylog space and 1 pass. And we show that if the edges arrive in an arbitrary order, we can achieve an of delta square edge coloring using n polylog space and again 1 pass. I'll specifically focus on the streaming algorithms in this talk because there's an obvious open question of whether an of delta edge coloring can be achieved in adversarial arrival streams, and also that the algorithms are pretty straightforward and easy to describe. So let's start with the model. We, as standard, assume that the edges arrive in a stream and we have access to n polylog words of a space that we can use throughout the algorithm, and we are allowed 1 pass over the input. But edge coloring is a little bit different from typical problems considered in the streaming model in that the output of the problem is as large as the input. We have to assign 1 color to each edge. So instead of storing this whole output into our local space, which is not feasible, we also assume that the output can be reported in a streaming fashion. And the challenge is that in this model, we cannot really remember all the colors that we have assigned to the edges so far. Yet we have to make sure that the algorithm reports a valid edge coloring and that uses a few colors. So let's see how we can do this. We start with the random arrival setting. The algorithm is pretty straightforward. We assign one counter CV to each vertex V, which over the course of the algorithm will denote the maximum color assigned to an edge incident to this vertex V plus 1. So initially this counter CV is 1. And in this example, for V, it's 5 because the maximum color incident to V is 4. Now, an edge between U and V arrives. We see what's the counter of its endpoints, which one is higher, and that's the color that we assign to this edge. And after that, we update the counter of each of its endpoints to this 5 plus 1. It is relatively straightforward to argue that the algorithm always returns a valid edge coloring. And to analyze the number of colors used, let psi be the length of the longest monotone path in the line graph, and monotone with respect to the arrival times of the corresponding edges in the input stream. We show that thus the value of psi precisely denotes the number of colors used by the algorithm, and using relatively simple probabilistic arguments, one can bound the value of psi by O of delta, given that delta is larger than log n. And if delta is smaller than log n, we can essentially store the whole graph into our input into our local space and report the delta plus 1 edge coloring. Also note that the figure shown in this slide shows that if the edges arrive in an adversarial order, this specific algorithm performs very poorly. In fact, if you continue this path and the edges arrive in the order of the path, you can use you will need to use n colors, while the maximum degree is only 2. Therefore, for the adversarial case, we need to come up with a completely different algorithm. Suppose that the graph is bipartite and that each vertex knows its partition a priori. And what we do is that we define one counter CV per vertex V, which this time corresponds to the number of edges seen for that vertex so far, plus 1. So the CV is initially 1 for each vertex, and upon arrival of each edge UV, we assign to it a pair of CU CV, and this pair indicates its color, And it's again simple to argue that the color of any two incident edges will be different. At least one of its entries of these pairs will be different, and that the maximum number of these entries can be delta times delta, which is bounded by of delta squared. And to generalize this to a general non-bipartite graph, we essentially just consider random bipartitions of the graph into log n levels and use the algorithm on each level independently from all other different levels.